switch a little bit the focus of the audience. Thank you very much for talking. IBM is also active in, let's say, first, I'm Michael Wirth, I'm Chief Technology Officer from IBM. I'm on international assignment from research and also fifth year in Russia. So we are active we are active also in Tatarstan, in Nopolis, and we are also signed last year at SPF in a memorandum of agreement for collaboration with Mr. Poltavchenko in St. Petersburg. So for us, it's essential that we collaborate with in a kind of triangle mode. With academia, who are generating the knowledge, source of innovation, with the industries, classically an industry, a commercial agent, a company, and with the government who oversees those topics that honored academician Agavanian has addressed. So our goal is to do two things in two dimensions, to improve financials and also to increase GDP if possible. But now I switch. We have to switch. This very serious topics what we have in a kind of environment that is totally different. Because there is IT in the background in the audience. Some of you are CIOs. I'd like to tell you where is IT going to be and what we can predict. Even though prediction, I think some of them are true. Not everything what's predicted is wrong. So cognitive computing is human-based, brain-inspired computing. And I'd like to show you where we stand. I'd like to make it quick. So, first one statement. You have here a statement from computers are useless. They can only give you answers. Statement of Picasso. And Picasso, you have to watch when he was living. He was living from 1881 to 1973. What age it has been that he was seeing when he was working as computers. Computers at that time had been totally different from the computers we have today. So at that time we were switching from boards from, these vacuum tubes into transistor age. In the 60s we had the first transistor, and in 71 we had the first integrated circuit, and that was the time frame where Pablo Picasso was looking at the computation. So I will take you now in a different age. This is what you see in here is big data environment. That's a picture from Manhattan on a Friday evening, and the blue lines you see in here are the transport lines made by GDP from a pizza delivery service. So behind big data, there is always business. And we try to combine data with business, take the right essence out of it, integrates the right data to make the right business decisions. So for some, this has a meaning. It has a meaning for travel agencies, it has a meaning for policy, it has a meaning for those who do business based on this transport of pizzas. And you know what you should do in a traffic evening or on a Friday evening with this. This here is Siberian forest in winter. No, it's not. It's a cut through a monkey brain. It's a tissue cut through a monkey brain. You see here the connections between neurons. The synapses, some of them are longer, and some of them are multidimensional connected with other neurons. We are studying this. This is neuroscience. We try to put the neuroscience in correlation to computational science. So we have worked 4 years to put this, what you saw before, into a mathematical model. So this is a mathematical model of a monkey brain. And if we take these mathematical models and aim it at the kind of synapses that a classical monkey or even human had, if the difference is not so large, we talk about 100 trillion synapses that are operating in real time. And this is where future computational science, cognitive science will go. So you can read about this. This was a task we did over 4 years, complete in 2010, mathematical model of a monkey brain. What we combine now in computational environment is we take the classical environment, which you see at the right side here. Switch, find it better. It's not pointing at the right side, then I can take the pointer away. See, it's right side systems of record, classical data systems. Classical data systems, all the data that was stored in the past, it's traveling, it's currently loaded into the system. On the left side, you have systems of engagement, the Internet of Things, where the data gets generated, sometimes stays at this point and will never reach a system of record. And at that moment data gets generated, you have to see in what kind of correlation will it be between historical data and the data we try to extract. So the system of insight is computational science, the right algorithms in real time to take the right business decision in real time out of this. You see how the data gets generated. These are charts that you may have seen in the past. This is kind of speed where data is generated and what kind of data we are generating. A lot of them is machine generated. 80% of today's data is completely uncertain. It's not structured data as we have seen it in the past. It's based on pictures, based on text, based on voice, and we have to put this data into context. The biggest challenge right now of big data analytics. And we try to put this in the structure. On the right side, you see our systems. This is a system of insights that we have in classical IT infrastructures where we put the kind of base infrastructure in place, the IT infrastructure that should manage it, and at the left side, the thing is constantly scaling up based on machine-generated data. And I show you the dilemma in which we are in the IT industry right now. 90% of the data has to be clean. Am I too fast or do you need translation? I don't have my microphone.
Too fast.
Too fast?
Yeah.
Too fast. Okay, good. I got 20 minutes to talk, so okay. 90% of the data has to be cleaned away because 90% of the data is irrelevant for making interpretations. So when we have structured data, when we get all the information out of the data, we work with 10%. 2% finally can be used in order to make business decisions. And if you look at what kind of data is generated, again, Internet of Things, another 90% of the data will never reach the backend, will never be stored in a system, will never travel even through a cloud at the end of a kind of system of storage, system of record. That means we have probably only less than 1%, 0.1% or 0.01% of data that is relevant for making business decisions. So we want to clean this away. And for this, we have invented algorithms, with algorithms that we call, let's say, cognitive science algorithms. I will explain to you one system that's behind that. Try to make it a little bit slow. But first, let me define what is cognitive computing, cognitive systems. It's a data that is interactive and it's based on natural language. It has to understand language, because text is language, voice is language, in pictures all the language is included. It has to be iterative and stateful. It has to work like a human brain is working. When I try to explain that only 90% of the data is relevant, that means 90% of the data can be taken away and can be forgotten. It's a human attribute of a human brain. So stateful means we keep forgetting and we keep learning. We take things away that we are going to see are relevant and put them as a new data point into storage, into the system of record. You have also kind of classical conflict between machine learning versus expert systems. The systems we have today have to go in a dialogue. They have to ask questions to the human being, to the experts. There's a dialogue between the expert systems and the artificial intelligence, which is machine learning. This is what we put into the current algorithms, into the software of our computational environments. So there are two approaches. The approach top, which we have from the systematic approach, where we develop the analytics as a software, and the other approach where we come from the bottom, where we try to develop the processes. Semiconductor technology is based on processor technology, where we try to be fast as possible to come to the right conclusion in real time. And IBM is doing research in 8 dimensions. We have around 3,000 researchers working, collaborating with a lot of universities, more than 1,000 universities in collaboration mode, and we generate per day around 20 patents. Last year we generated 7,335 patents, 22nd year in leadership among all industries. And I will talk a little bit about mathematical science and physics and behavioral science in a moment. Last 3 years we have focused on 4 thrust areas. One thrust area here in the middle is cognitive computing again, where we try to anticipate human-inspired computation. So what does it mean? I give you a task here. We have, in 2011, we have announced Watson. Watson is a name aimed at the founder of IBM, but it's also a name for a computing system that's the first computational computing system that was cognitive. It was looking for a dialogue with a human being and was trying to interpret on a certain confidence level results, answers. And in 2013, we have invented and announced a chip that we call Synapse. The Bluetooth noise chip is a chip that was working like a human brain does. And I will explain this also. Now this technology, what we are working, all of us working on today, for the last 40 years, is based on the von Neumann structure. I will not explain this because I take it as a given. And the von Neumann architecture is bus triggered, it's clock triggered, it's clock frequency triggered. So it's sequential. And this Watson was running as a deep insight algorithm on this classical von Neumann architecture. So I give you a challenge here. That's what this Watson computer was doing based on conventional architecture, on von Neumann architecture, was trying to find answers to questions humans were asking this Watson. Here you see what a computer easily can do. You see here a classical algorithm. Some of you may know whether the answer is positive or negative. So this is easy for computers. That's the answer. So further easy is if you put something in a structured environment and you have to look it up. Classical systems of record, scrolling through the systems with classical algorithms. This is easy for a computer. If we go and make lookups, very trivial. Now I show you the challenges. Here I give first a statement. Albert Einstein was born in Ulm. Lookup table. You can sort per person, you can sort per birthplace, and you can look it up. Very trivial. If it will be an unstructured environment that we have to scroll, for example, through a text that was written like here, one day from among the city views of Ulm. Otto, who was a friend to Albert, has chosen a watercolor for remembering Albert Einstein's birthplace. Now, if you give now the question to a computer, please answer where Albert Einstein was born, there will be a huge challenge because it has to be decomposed, structured, it has to understand the language, it has to scroll through a database that may have multifold results and connections, Ulm, Einstein, birthplace, and then there will be a confidence level generated to predict what answer it could be. That is a challenge for today's unstructured environment to take the data, clean it, analyze it, and predict the right answer. Same thing for Jack Welch, who was CEO of GE. If the answer is like, or let's say the question in this case is like, if leadership is an art, then truly Jack Welch has provided himself a master painter during his tenure at GE. For us who understand language, here in this case the English language, it will be easy to interpret that he could be CEO of GE. But for a computer who just has a sentence, it's a huge challenge. So what we have done, we have put this into algorithms decomposed based on language and syntax decomposition and predictive analytics. We have modeled this in 2011. We have generated the patent already in 2008 for the speech-based analytical algorithm decomposition. And we generate for potential answers to certain questions millions of hypotheses as potential answers. And these potential answers here on the left lower corner are considered hypothesis generation. Among this hypothesis generation, which have to include already the potential answer, we run through in real time, within seconds, through the potential likelihood of a given answer. If the answer gets a kind of confidence level that is above 50, 60, 70% that we can choose, computer will answer the right result with a confidence level. So this confidence level, if it's not met, computer will say no, I cannot answer. This is what we do today with software environments at cognitive computing on conventional architecture. This is where we are leaving right now, the environment of Van Neumann architecture. We have asked, for example, hypothetical questions to this Watson. I can give you one. We put this Watson engine today now in a dialogue, where this answer that was generated, let's say at an 80% confidence level, was stored at the backend in the systems of record as a new true finding. That makes it completely different from search engines, because the system at that moment gets learning. It takes no generation of data points. And this is where cognitive science develops constantly. So we use the answers found as a new data point, and then it continues to develop it further. If the answer cannot be provided, for example, at a confidence level that's enough, computer will ask, give me more information. Have you considered that? And then the dialogue starts with an expert. The only goal is to find the right answer and to store this point new. So we could have run two Watson engines, in this case, against each other to find the right answer. This is where cognitive science develops based on conventional structure. So we have done, for example, many other things. I have a calendar here. This is a calendar for 2015. We have given Watson a task, can you generate, based on knowledge that you have, potential, let's say, cooking results. Can you cook certain dishes as a dessert, as a main dish, or as kind of entree, based on certain expectations what the human taste would be? We have given him the task to cook, and he came up with recipes for desserts, for main dishes, etc. This is in Russian, and you can take them away later. Now I show you the dilemma of where we are. This Watson was running at a classical scale of 10 to the 14 synapses, or 10 to the or 100 trillion synapses. And it was running in real time, but it consumed already, based on von Neumann, lots of energy. So where we are on the right side, you see the development of conventional computation. If we try to build up a human brain today, and we have done this in 2010, a human brain would consume 12 gigahertz on conventional von Neumann architecture of power. We have done this in 2010, and it was with conventional architecture 1,000 times slower than a human brain. If you want to do it in real time, as I said, 12 gigahertz of power. That's all power what Mosanago can generate here in Moscow. So the brain, if you put this also in perspective, runs at 12 to 20 watts. Big offset. Try to simulate this. We expect this to be done in around 2020, 2025, to simulate a human brain in a let's say 1 liter box with around 1 kilowatt consumption and 100 trillion synapses functionality. And we have developed a chip that is called Synapse chip that has eliminated the von Neumann architecture, is not running on bus, not running on clock frequency anymore. It is a completely free, let's say, spike or incident-triggered architecture that we built in 2013, and this chip is consuming only 70 watts or milliwatts of power for around 256 million synapses. So if you want to do it and roll it up to human brain scale, it's 100 trillion synapses. It would need 400,000 of those chips. These chips would consume then around 30 kilowatts of power. It's a huge improvement compared to the 12 gigawatt we had before. So we are on a roadmap here. We developed this chip over the last 10 years. We try to overcome von Neumann architecture, put this with the algorithms together, get it into low power consumption, get it on a high-speed mode, get it in a dialogue, and have a learning environment like a human brain in the nearest future. And that is where we are running, based on computational science, to assist decision makers with the right decision, cleaning data, getting into dialogue, recommending at a high confidence level the right answer, and still have it on the power environments that we can afford to pay and install. I'd like to stop here because this is what is the dilemma, what we see right now in computations and cognitive sciences. We will overcome with this technology the speed of human evolution. So the technology is at a path where in the next 10 to 20 years we'll be able to simulate human brain, to have brain-inspired computation reality. That was high speed.
Thank you. Извините. У нас сейчас будет время для вопросов, а пока прошу специалистов наладить следующее выступление у нас по скайпу. Questions, please.
Можно по-русски?
Да.
Скажите, вот синапс появился...
Сейчас наденьте, а что просто открываешь. Да, пожалуйста.
Синапс это принципиально не фон Нейман. Но Вотсон-то был до 2013 года еще построен, синапсов еще у вас не было тогда. Тогда Вотсон работал на базе фон Неймана.
Yes, that's what I said. Watson was based on von Neumann, and it's still. So it is significantly slower. It has the conflicts that we all know. If I described on the right side the data infrastructure, the IT systems infrastructure, it was not running on the cloud. We had to put all data into Watson at the time, and it was consuming tons of power. We had 96 Blue Gene racks installed with a 500 terabyte of data, 1.5 teraflops. So it was huge power that we consumed at that time. It was conventional, but it will never be at a point where we would assume it is as fast as the human brain can be. And I show you cognitive science in a way where it will go to. Watson was conventional, von Neumann, yes. And it will be for the next probably 10 years or even longer.
Еще вопросы?
И синапса не будет в Вотсоне. Вот это
Senat, I showed you the top-down effect. On top, IBM is developing systems, services, algorithms, huge amount, 75% of our business. And at the bottom, we come up with the systems themselves, which are based on von Neumann still, high processing power, high integration, 10 nanometers, etc. What we do in silicon technology, so also trying 45 nanometer technology. And we are building up a new technology that eventually will run with the software developed that we use in cognitive computing in Watson and combine the two things and have in future such kind of Watson capabilities in a small volume, low energy. That's the future. Two things totally uncoupled, but software will be reused. It's a different environment. Does this answer your question?
Спасибо. Еще у кого-то? Thank you.